Yes, sir. So this is chapter 9 in syllabus. We are skipping. Uh, yes, sir, please. So we are skipping chapter 7 and 8. Okay, we'll come back to that later, sir. Okay. So so we'll just recall what we have learned about electricity in IGCC. Okay, sir. So the first thing is electricity is flow of charge. Okay. So right here we are going to bust a myth that people think electricity means only electrons. Okay, it's not. Even if just a hydrogen atom, positive hydrogen atom, if it moves hydrogen ion, then it is also electricity. If OH minus moves inside the water, it is also electricity. Any charge, if moves, it's electricity. Okay. Um, but mostly this has to deal with the electrons. So yes, electron also an electricity, but in general, it's just flow of charge. Okay. So so when there are multiple charges flowing from one point to another point, then we call it flow of charge carriers. Okay. So so this is the definition of electric current. Electric current is flow of charge carriers. This can be anything, but mostly it's electron. Yes. Okay. Yeah. So then we will learn about this charge. What is this guy? Who's this? So we are so far not clear what is charge, but we have an idea how it behaves, what are the properties, but we cannot. For example, we can define what is a force, but we cannot define what is a charge. All we know is it is quantized. Okay. So so the charge is a physical parameter or a quantity. Okay, it's a scalar. Okay, its SI unit is coulombs, capital C. Okay, this is a SI unit. This is not SI base unit. Okay, so charge is not one of the 7 fundamental units, fundamental quantities. Okay, charge is a derived quantity. Okay, it is derived from I equal to Q by T. From this equation, we can derive charge as I into T. Okay, so 1 ampere for 1 second is 1 coulomb. So it's just ampere second. So in real life, 1 coulomb is a very big number. Okay. Okay. So what do we know is about one of the properties we call polarity of charges. Okay. So we know that charges can be classified into positive and negative. Again, this is completely just crazy idea from Benjamin Franklin. Okay. It's arbitrary. We don't know whether it's positive or negative for sure. It's just arbitrary. Okay. So, but we can understand that group of charges behave this way, so they are negative. Group of charges behave this way, so they are positive. And they, if you put positive and negative, they like each other. If you put positive and positive or negative and negative, they hate each other. That's all. So based on that, we understand, okay, polarity of charge exists. Okay, so this is first behavior. Second behavior, it's quantized. So what do we mean by quantized is, so this the fundamental idea of whatever it's called quantum meaning, that's the least. You can't go further in numbers or counting. For example, when someone asks the question, how many how many persons in this room? Can the answer be 6.5? No, it can be either 6 or 7. There is no way that we can address a classroom or any room. Number of people in it are half, because how do you define half people? Yeah, yeah, it's not possible. Similarly, charge also cannot be quantized further than this value. Okay, so this is small q. What is this charge? for protons and electron, charge of fundamental particles. Okay, so this is Q. So we really interested only in the magnitude. We don't worry or care about the sign. Okay, so we care or worry only in the atomic physics. Otherwise, you can just wherever we work, we just work for the magnitude. Okay, a nice question though. Yes. So this charge is n number of uh, charges versus fundamental charge. Not versus, multiplied by. Okay, this fundamental charge is 1.6 into 10 power minus 19 coulomb. Okay, so this n is number of charge carriers. So how many number of charge carriers in particular volume? That's what we will call it as a number density in A level. How many number of charge carriers in a particular volume? That's what we will call it number density in A level. Okay, so in DC circuit also we will have that one, but in A level we will stress that point very much. Okay, yes. Okay, so once this is clear, what do you mean by this? If you count charge in a particular system, you can say maybe 1 into it's 1.6 into 10 power minus 19 or 2 1.6 into 10 power minus 19. We cannot say 0.5 10 power 1.6 into 10 power minus 19. That's what we mean by quantization. Okay. No, it can be half a coulomb, but it cannot be half of this one, 1.6 into 10 power minus 19. Okay. For example, it can be 3.2 into 10 power minus 19 or what is 4 into 1.6? 6.4 into 10 power minus 19, because you see these all are multiples of 1.6 into 10 power minus 19, but it cannot be 3.3 into 10 power minus 19. Why? This is not a multiple of 1.6. Do you see this point, sir? Yeah. Okay, a small calculation here. If one charge, okay, is 1.6 into 10 power minus 19 coulomb, how many charges in 1 coulomb? Do you understand the question, sir? Yes, sir. How do we address? 1 coulomb is n into 1.6 into 10 power minus 19. Okay. So n is 1 divided by 1.6 into 10 power minus 19. So it's simply 1 divided by 1.6 into minus 19. So what we get here is 6.25 into 10 power 18. So this is a pure number. This n does not have units, sir, because it's a number. Okay. So what do you mean by this is, when we say 1 ampere current, okay, it's 1 coulomb per 1 second, right? So meaning that 6.25 into 10 power 18 electrons has passed in 1 second. That's what we call it as 1 ampere current. Okay, so that's the idea. Yeah. Okay. So now, so far in ITCSE and lower grades, we have just worked with what is I, and now we understand how many number of electrons flow in I, right, sir? Now, if number of electrons given So how to find uh, current? Okay. Do you understand, sir? If number of electron given, how to find the current? This is the question. This is what we want to address here. Okay. Now let's take a wire. Okay. Whose cross-sectional area is A, whose length is L. And let's say that if number of electrons are given, how to find what is the current? Okay. So this is a question. So we try to address and find an equation, that's all. Okay. So we know that I equal to Q divided by T. Okay. We'll keep it there. Now, if N is number density, okay, meaning it's number of electrons. Okay, we'll call it number of electrons given in unit volume, right? Okay, so we know that, sir, this is N subscript E. Okay, maybe I'll put apostrophe. So number of electrons in unit volume. Okay, so now, so this is charge divided by time. Okay, so can I write this N into V? So number of electrons into volume, right, sir? So that's the number density is number of electrons divided by volume. So what is number of electron? Number density into volume. Does it make sense, sir? Okay, I'll repeat one more time. What number density is? Number of electrons in unit volume. So number of electron is number density into volume. So N into V. Make sense? Okay. So now we know that I equal to Q by T, and this Q is N into E, right? Number of electrons. So divided by time. Okay. So for this number only we have worked this. Okay. So instead of N dash, we are going to write N into V E divided by T, right, sir? Okay. Now, so can you see that the cross-sectional area is A and length is L? So what do you make volume out of it? So this is capital V, volume. Okay, so I'm going to replace it here. Equal to capital A into L into E divided by T. Okay, sir? Okay. So we have N by T, A by T, or L by T, E by T. Which you will change if you can. No I here. No. Yeah. Is there a Q here? Sir, this N is, okay. Now this is the number of electron. This is just number density. How about L by T? What is length by time? What is distance by time? Ah, so L by T is V. Okay. What is moving here? So this V is what we call it as. You have to please take it for granted now. We call it drift velocity. Okay, I'll explain in a minute. Okay. So I equal to N A Instead of L by T, I'm going to write V subscript D and E. Okay, wow. This Vd is what we call it as a drift velocity. Okay, sir. Mm. So in this case, we used E for electron. If you use something else, you have to replace it with Q, general term. Okay, so Q for anything you want to use. Okay, so now we have to understand why this is not a normal velocity but drift velocity. Okay, so now let's take a conductor and zoom in. Is there empty space inside? Lot of empty space, yes, because we know that atom is mostly composed of empty space. But problem is, can electron freely move inside? Okay, let's say that it can freely move inside. So as soon as we apply a potential, okay, instantly it should go from this end to that end, right? But is that happening? Is that what happens? What stops it? Okay, one other electron, but all the electron going to move in the same direction only. So probability of, yes, it is there, but what else will affect? Okay, length is also a contribution to this one. So it will actually collide with other electrons, also the other ions inside, right? A metallic one. Mm. So what do we call this collision? Resistance. If there is no collision, no resistance, right? So these collisions indeed results in resistance. Yes. Mm. Yes. Okay. So we figure out the electrons are not instantly going from this end to this end because it has to come across this resistance collisions. Okay. And if you take one electron, is it going to travel in a straight line? In which way it will travel? So can we use like zigzag or something like that? Okay. So this is very random. So but we have declared velocity is only in this direction, length divided by time. So in this direction, how much it is moving? That's what we are interested in. So in any particular point, if you zoom into let's say that we can see the electron, then it will be just randomly moving, right? So its average velocity will be zero at any instant because it's just randomly moving back and forth. Okay. But eventually, this electron passes from one end to another end with some speed. That's why we call it as a drift speed. If you look at in one particular point, it has some different velocity that's close to zero. But overall, if you take, it is going with some velocity. That's what we call it as a drift velocity. Is it clear, sir? So maybe you can take the little meaning drift. It's like, you know what is drift in car, right? Wheels spin one direction and then the car moves in the other direction. So the electron they collide and they move in one direction, but in the end, the result they move in another direction. Okay. Yes. So this is not actually what happens inside, but we can uh, take as an analogy and then understand what is happening inside. Okay, sir. Okay. Sir, let's take a container of gas. Okay. What is the velocity of the container? Zero. But is this the same for the particles inside? No. The particles are keep on moving, but they are not getting anywhere. So it's a complete random motion. They have instantaneous velocity, but if you take after some time, they remain in the same place. Okay, inside the container, yes, they have velocity, but if you take as zoom out as a container, they don't have. Same, whether you apply the current or not, the electrons orbit and the path is very random. Okay, so only if you apply potential, they will migrate from this end to this end in linear motion. Okay, yes, yes, sir. Okay, so then we have to address one more point here. Third one, the charge is conserved. Okay, a system can be neutral, meaning number of positive charges are equal to number of negative charges. Okay, but you cannot destroy or create a charge. So number of positive in a system, if there is something, it exists same. Okay, that's all. Even if it is neutral, mean number of positive is equal to number of negative. That's all. You didn't destroy one positive to negative. Okay. So in nuclear physics, we will learn uh, one neutron split into proton and electron. Okay, that has to do with the quark. Okay, so that yes, that is different. Okay, yes. So we understand its polarity of charges. We have positive and negative. Charges can be it's quantized. You cannot split or divide in 1.6 and 10 power minus 19. And number of charges conserved. Okay, sir. In a closed system, particularly. Yeah. Okay. So having said that, um, so this is positive side of the battery and this is negative side of the battery. Which one is positive? Which one is negative, sir? Are you sure? Check one, sir. I'm a little confused about this one. Every time I get confused. Okay, let's take it for granted. This one is positive and this one is negative. Okay. Mm. Yeah. So this was the direction of the current was given before the understanding of the electron. Okay. So it was understood at that time current flows from positive terminal to negative terminal of the battery. So this is what we call it as a conventional current. Yeah. So this is from positive to negative. In other words, direction of positive charge movement. This sentence is very important. Conventional current is the direction of the positive charge movement. Okay. So the opposite is actual current, electron. So in the case of electricity. Yes. Yes. Okay. So this direction of positive charge movement is very important because whenever you use Kirchhoff law, whenever you use deflection in magnetic field, whenever you use Fleming left hand rule, right hand rule, we always follow the direction of conventional current, direction of the positive charge. Okay. So yes, direction of the positive charge. Yes. So if you happen to trace beta particles direction or electrons direction, you will take the current as a opposite direction because they are moving negative. So in which direction current is moving? Opposite direction. Okay. So this idea is very important. Most people they don't see this statement and they make mistakes in magnetic fields and electric field, how they deflect. Yes, sir. Okay. one last thing about fundamental is electricity for positive, negative, battery, current. Yeah, okay. So if I miss anything, we'll come back. No problem. Yes, sir. Okay. So uh, a quick recall about current is done here. Now, so we have to understand what is potential difference. Okay. So the definition of potential difference is energy transferred per unit charge. All these words must be present in the paper, sir. Okay, energy transferred per unit charge. If they ask, across the component, then you add the word across the component. Okay. So instead of across the component, if you use the word across the circuit, energy transferred per unit charge across the circuit. That's what we call it as a EMF. Okay. So this potential difference V is energy per charge. Okay. Yes. So so V is PD, potential difference. E is energy. Q is charge. Okay. Yes. So now can you see that E equal to V into Q, sir? Okay. So V is measured in voltage. V EMF also measured in voltage. Okay. So can you see that E energy is voltage into charge. Okay. So can I just give one unit? Joule is equal to voltage. Okay. V into charge E. So this is EV, electron volt. So joule also can be measured in electron volt. So electron volt is also unit of energy. What do you mean by 1 electron volt is you take 1 electron and leave it between 1 volt. Okay. It will accelerate and gain energy, right? That's 1 joule. Okay. That's the idea. So actually 1 electron volt is 1.6 into 10 power minus 19 joule. This idea is also very important. This is very effective and very essential in nuclear physics. Also quantum. Yes. Okay. Yeah. So I think we know. Okay. So we will work out the unit, SI units later. We know that power is energy by time. Okay. And we know that energy is potential difference into charge. So power is potential difference into charge divided by time. What is charge by time? So Q by T is I. So power is V into I. Sir, we are talking about power. So power loss also the same equation. Power transferred through the electricity also same equation. Sometimes people think that they have different equation for power transmitted. No, it's the same equation. Yes. Okay. And if I replace V into I, okay, V equal to IR, then instead of V equal to IR, then I put I into R into I. So I get I square R. This is also same equation. Okay. So from V equal to IR, if I take V divided by R, P equal to V into V divided by R. So P will be V square by R. This is also same equation. Okay. But let's say that I want to transfer from one place to another place through a wire. Okay. Now we can do two things. Okay. Whatever the power I am sending here, I'm going to receive the same power. Okay. So that's how basically the transformers work. You will just send the same power, but you will play with the voltage and current. Okay. Now I have two options or ways to do it. One, I can increase the current. Even if I increase the current, obviously you have to decrease the voltage. Then only the current will increase, right? So P equal to V into I, right, sir? So if you either you have to increase the voltage and decrease the current, or you have to decrease the voltage and increase the current. Same power. Do you understand this one, sir? If you want to have the same power, you can play with voltage and current. But if you touch one, other will change. Okay. So if you increase the voltage, current will decrease. Yes. The battery is providing energy, right, sir? Battery is providing energy. Rate of energy, how it is delivered, its power. Okay, wow. Now if you switch for the higher battery, then you can increase the power, higher energy. If you switch for the lower battery, you can reduce the power. Depend on the battery, depend on the source in this case. Okay. Yes. Now, so let's say that I choose to send high current and low voltage. Okay, maybe higher current and lower voltage. Okay, wow. So if higher current means more resistance or less resistance? Ah, so if you send, for example, we know that rewrite this equation, V by I equal to R, right? No, yes. Yeah. So V into 1 by R is equal to I. This is how. Okay. Actually, what happens? More current means more charge carriers flowing, right? More charge carriers flowing means more resistance. So the wire will heat up. Okay. So if you take this equation, power is I square into R. Already you are sending higher current and your resistance also going to increase. So power loss will be higher. Okay. But if you choose to send lower current and higher voltage, okay, as you increase the voltage, resistance will decrease. So higher the voltage, faster the electron can travel, but fewer electrons will travel. Yes. Okay. So, but look at the power when voltage V square by R. So it's here it is divided by resistance. Also the resistance is decreasing. Okay, less resistance. Here it is multiplied by resistance. Also the resistance is increasing. So the power loss will be higher, very high in this case. Power loss will be very low in this case. So that's why in Power grids. Have you seen the huge towers? They will send cable. They have higher voltage. They will have 5 lakh voltage, 50 kilowatt. Or in train, they will have 25,000 voltage, 25 kilowatt. Because higher current means you cannot send it for long distance. Yeah, more power loss, and also you have to make the wires thicker. It will increase the amount you spend to build structures. Yeah, heat dissipate. So higher voltage is optional. So that's why they always less resistance and less power loss. But more voltage is more danger. Yes, sir. Yes, yes. Yes, yes. So eventually it will build up. Yes. Hmm. It will increase the temperature also. Hmm. Okay. So we'll put this in a nutshell. Okay, sir. So high voltage, so less resistance, less power loss, lower material cost. They will ask this question, sir, why they send high voltage, or whether it is advisable to send higher voltage or higher current in the last part of the question. Hmm. Is it clear, sir? Hmm. Yes. Okay. So now we will play with units. So we have come across this Q by T and B equal to I into R and E equal to voltage is energy by charge. E equal to Q into V, P equal to V into I, P equal to I square into R, P equal to V square divided by R. Okay. So these are the equations in electric current and potential difference. So we still to go with resistance, but okay. Now find the SI unit of charge. Uh, so ampere into second. Okay. So SI base unit of charge is ampere into second. Okay. Find SI unit of voltage. Mm, mm, okay. There are multiple ways you can. If you don't know R, avoid this equation. You know about this equation, right? You can take any equation. Mm, mm. Okay, twice. S is coming twice. Mm. Okay. Okay, no problem. So V equal to E divided by Q. Okay, ma'am. We know that energy is joule. That is kilogram meter square second power minus 2. Right? divided by charge is ampere into second. So voltage will be kilogram meter square second power minus 3 ampere. Now, yeah, my ampere inverse. Okay, sir, that's voltage. Sir, this is very important because recently they are asking in MCQ, also the first chapter. Give the SI unit of this homogeneity. Mm. Okay, okay. Third, we will work for resistance. Find the SI unit of resistance. Super. Which equation you use, sir? Okay. So V equal to IR. So R equal to V by I, right? So you should have used kilogram meter square second power minus 3 ampere inverse divided by, instead of I, you can use ampere. Okay. So R, you should have got kilogram meter square second power minus 3 ampere per minus 2, right, sir? Okay. Now V equal to IR. So, um, so now it will not make that sense, but one, you will learn capacitance. Okay. So maybe I'll give the equation. Okay. So capacitance, C equal to Q divided by V. Find for capacitance. This is not Coulomb, capacitance, Q by V. Mm. Yes, Q is a charge. Mm. So Q you should have used A, yes. For V you should have used kg meter square second power minus 3 ampere inverse, right? So you would have got kg inverse meter power minus 2 s power 3 ampere power 2. Sorry, s power 4, right, sir? No, it's A inverse, sir. If it goes, it will. So I should have got s power 4, right, sir? Sir, these homogeneity equations are very important. This is how they make mistake and lose marks. Okay. Now, interesting factor. Find what is R into C. Capacitance. Yes. This one, sir. Mm, mm. Super. So we know that R is kg meter square second power minus 3 a power minus 2 into C is kg inverse m power minus 2 s power 4 a power 2. So kg inverse m square m power minus 2 a square a power minus 2 Okay, s power minus 3, s power 4. So remaining you have only s. So this RC will have unit of time. So this is called a time constant of a capacitor. Okay, so this is very useful in A level. Okay, yes, sir. Mm. So this is how we should work for. One more thing we can work, just one more thing. Okay. Uh, okay, no problem. That we will cover in A level. Yeah. Okay. Is it clear, sir? This unit and this case, yes. Okay. No, no, we don't have, but in A level they will provide what is the unit of capacitance and they'll ask you to derive. Mm. Okay. Yes, sir. So finally we have uh, resistance and resistivity. Okay. So first we have to use define what is resistance. Okay, super. So the Google definition is this: opposition resistance is the opposition a material offers to the flow of electric current. Yes, caused by the collisions of electrons with atom. Okay, so as we discussed already, so this resistance is denoted by letter R and measured in ohms. So this is called capital omega. Okay, so this is instead of ohms. Unit of resistance is ohms. Okay, now we know that V equal to IR, and so this IV characteristics of the following elements are very important. One minute. I can write the same thing. So whatever we have discussed. Okay, so this IV graphs. Okay, V equal to IR, right, sir? So if I rewrite this equation, um, okay, I equal to 1 by R into V. Okay, sir. So can you see that this is in Y equal to mx plus C format? C is 0 here. Okay. So if you have a graph and I is in Y axis and voltage is in X axis, the gradient is 1 by R. Okay. So this is very useful in practicals. Okay. Yeah. So for any graph, for any component, if you take I versus V, I in Y axis, V in X axis, the gradient is 1 by R. Okay. Whether it's a straight line or, yeah, whether it's a straight line or not is our problem later. But in the graph, the gradient is 1 by R. Okay. So, so the first one is, first IV graph is metallic conductor at a constant temperature. This constant temperature word is very important, sir. Okay, so why metallic in a constant temperature is in a constant temperature. Okay, normal metal, sir. Metal, any metal. Okay, so if you draw the V versus I graph, then it will be a straight line. Remember, when voltage is zero, current is zero. It's a straight line. Okay, can you see the resistance is uniform, the gradient is uniform? Okay, so whichever conductor gives a straight line in IV graph, we call them as ohmic conductors. Not always. If the temperature change, they behave differently. That's why we add the word constant temperature. Yes, you should see the gradient. You should see the gradient of this graph. If it's straight line forever, then it is a ohmic conductor. So that we will see what is Ohm's law. Okay. So second one is semiconductor diode. Yes, sir. Okay. For this semiconductor diode, the idea is okay. So there are this depends on type of diode, sir. Okay, but we will have a general, very generic curve. Okay, so it look like this. Okay. Uh okay. Sorry, sir. This part no, must not be there. Okay, so only this red part. Yeah, it should be just straight line here. It should not be curving. Curved. Maybe I'll draw one more curve. Okay. So semiconductor, something like this. Okay. Again, the curve depends on what type of diode it is, sir. Okay. The curve depends on what type of diode. But what we understand is it just allow the current only in one direction. Even if you apply voltage in opposite direction, it does not allow the current. Can you see the current is zero in the opposite direction? Hmm. So only if you apply the voltage in positive direction, the current increases. Yeah, if you just reverse the polarity, then it will be negative. Okay. Yes. So now because what is a diode? Diode allows current only in one direction. So if you apply voltage in that direction, current will flow. If you reverse the polarity, if you even if you apply the voltage in opposite direction, current will not flow. Yes, sir. Is it clear? Yes. But however, in real life, small current will flow in opposite direction if you take a bigger diode. Okay. So that's why, but you can take theoretical value. In left side, it is zero. Yeah. No need, no need. No, I'm just telling you extra information. Mm. Yeah, yeah. Very small, very small. Mm. Okay. So finally, it's a filament lamp. Okay. So in filament lamp is actually this graph. Okay, filament lamp work even in opposite direction. Uh, okay. Yes, sir. No, no, filament lamp. I'm going to draw it here. Okay, so filament lamp is this. Mm. So can you see after sometimes, even if you increase the voltage, the current stays same? Because if you keep on increasing the voltage, more current will flow for some time. But this current will also create resistance. So it will limit how much current it can pass. Yes. Okay. So this filament lamp, can you see this filament lamp give light because of the temperature? That's how this, yeah. So the temperature increases because higher current, and eventually the current saturates whatever the potential you're applying extra, that converts into energy. Okay. Yes, sir. So that's why, so I'm reading this, understand this one. The resistance of a filament lamp increases as current increases because its temperature increases. Mm. Yes. Mm. Yes. Okay. Now, so we discuss in whatever the conductor, okay, in whatever the conductor, voltage is proportional to current. We call those conductors as Ohm's law. Sorry, ohmic conductors. In whatever conductor, in whatever material, voltage is proportional to current. If you increase the voltage, current should increase. Okay. These conductors are called ohmic conductors. This law is called Ohm's law. Okay. So what is Ohm's law? In a constant temperature. This word is very important. This works only in a constant temperature. If you change the temperature, current will become saturated. Okay. In a constant temperature, voltage is proportional to current. What is the proportionality constant? What is it? K. Yes. So V equal to Ki. This K is, yeah, actually, so it will come like this. I equal to K into V. I equal to 1 by R into V. So V equal to IR. Okay. Yes, sir. So this proportionality constant is what we call it as resistance. Mm. So this resistance, it has its own idea and method. Okay. So this resistance is proportional to length. If length increases, the resistance will increase. This resistance is inversely proportional to area, because if you have more room to go, you will go with less resistance. Okay. So you take a conductor whose area of cross section is A and length is L. Higher the length, higher the resistance. Lower the area of cross section, lower the resistance. Sorry, higher the area of cross section, lower the resistance. Okay. So in general, R is proportional to L by A. This proportionality constant is what we call it as resistivity. Rho, rho. Okay. Can you find the unit of rho, sir? Hmm. Okay. First, no need to find the SI base unit. Just tell me, R is measured in ohms, L is measured in meter, A is measured in meter square. Tell me what is the unit of ohm? Sorry, resistivity. Hmm. 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 Yeah, so it's ohm meter. So resistivity unit is ohm meter. Okay. So this SI unit of resistivity is resistance into meter. So for resistance, I think we can just we will not derive again. Resistance is this kg meter square. Okay, kg meter square second power minus 3 a power minus 2 into meter. So resistivity is kg meter cube second power minus 3 ampere square. Okay. So you can just note down, but whenever you need, you can derive by yourself. Hmm. Okay, sir. Hmm. Then we need to understand two more devices in this fashion. So one is LDR. So light dependent resistor. Okay. So the statement is very important. And symbol for LDR. Do you know the symbol for LDR, sir? Yes. Yeah, by the way, LDR is this one. Arrow marks towards in. Okay. Hmm. Yes. So thermistor is this. Okay. First LDR, then thermistor. So thermistor is this. If just arrow mark, then it is a variable resistor. Mm. Yeah. So for thermistor, no arrow mark. Okay, sir. Yes. For thermistor, no arrow mark. In the syllabus document, no arrow mark. Super. Okay, sir. So in LDR, the resistance of LDR decreases as light intensity increases. How does this work is, once you shine the light on it, it will eject more electrons into the circuit. So resistance will decrease. More charge carriers available. Okay. So the thermistor, we have PTC and NTC, positive thermal coefficient, negative thermal coefficient, but we follow only NTC, negative thermal coefficient. Okay. So resistance of thermistor decreases as the temperature increases. Okay. So this is called NTC, negative thermal coefficient. Because can you see as the temperature increase, resistance decrease. There is something called the PTC also, but that is not in the syllabus. Yes. Yes, sir. So okay. So that's a. Mm. That's in NTC. Yes. Mm. Mm. Okay. Yes. Okay. So that's all with the syllabus chapter 9. We'll just I just want to do problems only with this one. R equal to rho L by A. Ah, yes, sir. Yes. Yes, sir. Okay. Uh, yes. So problem set 1. So problem using this formula. Okay. So first simplest. Uh, ah, sure, sure, sure. Yes, sir. Yes, yes, sir. So first simplest. Okay. So a wire has 5 ohm resistance over 1 meter. Okay. If the same wire is cut down into 0.5 meter, what is the resistance across it? Mm, mm. Okay. So this will be 2.5 ohms. This will be 2.5 ohms. Okay. In IGCSE, do you remember we have learned series and parallel resistors? Okay. Now if I connect these two wires horizontally, what will be the combined resistance? Mm. Okay, sir. Mm. So this will be 1 by R. So R will be 2.5 divided by 2. Mm. Can you see how it from 5 ohm to come 1.25 ohm? But what do you think? What with respect to the formula? What happens here? Initially, it's the same wire. We didn't do anything else, right, sir? We just cut the wire and we put them into parallel. Why resistance was from 5 ohm to decrease to 1.25 ohm? Ah, then what else is one length is decreasing? Then what else is happening? Now, resistance decreases as it's a result, right, sir? One contribution is length decreasing. What else? A no, area of cross section increases because initially it was only one wire. Now you have kept two wires side by side. So it's twice the area. It's a twice the area. Okay, sir. Hmm. Is it clear, sir? Yes. Okay. So this is very easy numerical problems, but they will not give very easy numerical problems. Okay. So maybe we'll do little complex problem. So 2. Okay. Wire has length L. Okay. And radius R. Okay. Now, if the same wire is melted and made a new wire twice the length. Okay, if this guy's resistance is R, what will be the new guy's resistance in terms of R? Do you understand the question, sir? Very simple question, but very complicated in answer. Do you understand the question? We take the wire whose length is L, radius is R. We melt the wire. We do not add, we do not cut. So we make the wire, new wire, twice the length. No, it does not. Your idea is right. R decreases, but how much it decreases? Yeah, I think you're right. Okay. But tell me how it decreases. Now, what quantity is not changing from the first one to second one? Resist, uh, resistance will change, sir. Resistance is what we want to find. Okay. Volume of the first wire and volume of the second wire is same. Can you see? Same volume only we are melting and making other wire, right, sir? So the volume of first wire is L into R. The volume of second wire is also maybe L dash into R dash. Okay. Now, so we know that volume of second wire is volume of the first wire. So V is V dash. Okay. Now we want to find what is R dash because R dash is not given. Okay. So how do we find? So L into R is equal to L dash into R dash, right? But we know that L dash is 2L. So L into R equal to 2L into R dash. So we can cancel L and L. So R dash will be R by 2. Okay. Yes. So what we need? Resistance. So resistance of the new wire. So rho into L dash divided by A dash, right? So with is the rho is going to change because it's resistivity. Resistivity is the intrinsic property of the material. I forgot to add it here. Okay. So this resistivity is intrinsic property of a material. Yeah, is intrinsic. 1 minute, sir. What do you mean by intrinsic is if you change the shape or size, it will not change. Okay. Resistance is an extrinsic property. It depends on shape and size. Okay. So if you change the shape or size, resistance will change, but the resistivity will not change. Okay, sir. Is it clear? Yeah. So the resistivity of the first wire and second wire same. Why? Because they are made up of same material. Okay. So now I'm going to write rho. Instead of L dash, I'm going to write 2L. Instead of A dash, what you will write? The whole square. So it will be rho into 2L divided by pi R square divided by 4. So this 4 will go into numerator, rho into 4 into 2, 8. 8 L by pi R square. Okay. So if I just take this 8 out, so 8 into rho L divided by pi R square. So what is this? This is just resistance of the first guy, right? So you will have 8 times resistance of the first. 8 times. Why? You have increased the length twice. Further 2 times it will increase. You have reduced the radius into half. For that 4 times will increase. So totally 4 into 2, 8 times. Yes, sir. This is the most complicated question because you have to keep in mind it's not proportional to r by 2, it's proportional to a. So it's proportional to r square. Mm. But sometimes they give you with diameter, sometimes they give you with fixed volume. But whatever it is, this is the most complex problem. Okay. Do you happen to follow this problem very easily, sir? No problem, right? Yes. So if you can follow this problem, you can solve any questions in resistance, this type of question. Okay. Yes, sir. Uh, okay, we'll finish with this now.